My name is Daphne, and today I will be walking you through speech recognition via FPGA network. For the purpose of this project, we are defining speech recognition as receiving an English sentence, dividing up the sentence into words, and identifying each word by calculating their most likely match in a dictionary of words. Speech recognition is a very popular area, however, it is mostly implemented in software. The goal of our project is to implement it in hardware. Now I would like to walk you through our architecture. We have several desktops that will be sending speech recognition requests to Load Manager. Simply put, they will be passing in a request. The Load Manager, in a round-robin fashion, assigns each desktop to a compute FPGA. Each compute FPGA receives the audio wave from the desktop and then processes it, identifies the words in the sequence, returns it back to Load Manager, which displays it on VGA. With that said, we will be moving on to the explanation behind the processing that gives us the words identified in each sequence.
Hi, my name is Dan. I'm from Group 5. I'm going to walk through our speech recognition algorithm that we use for our hardware project. I've broken it up into a couple of steps. So the first step is what we call word clipping. We get a word that looks like this white line representing the word signal, and we define a upper and lower threshold beforehand. In order to calculate the envelope of the word, which is this green line, we calculate the absolute value of the word signal and then a moving average, and that gives us roughly this green line. It's a simple envelope. And then to identify the locations of the word, first we check for locations where the lower threshold has been surpassed by the envelope and the upper threshold has been reached. And then we wait for the word to end, which is when the lower threshold is reached again. This gives us boundaries to clip, so we have the beginning, the end, and then again. So in this example, there are two words because the envelope goes up, down, above the upper threshold, and then hits the lower threshold again, and then does it again. So there are two words. We then frame a word, so once we've excised just the word, we chop it up into regions that are roughly 20 to 40 milliseconds in duration. And so this is what one frame would look like. So we have 64 of these, and then this is for illustrative purposes what the next frame might look like this. So we just multiply the index by or we multiply the non-interested parts by 0. So this would be for I equals 2, this would be for I equals 3. Do this all the way between 0 and 63. The next step is, this is the FFT step. So we pass this frame into the FFT, which will generate a spectrum between 0 and a large number that depends on the sampling frequency. We're not actually interested in this region here because it's not that informative for regular speech and quite frankly uses a lot of resources, so we just trim at 4 kilohertz. Most speech is contained in 4 kilohertz. We then window the frequency spectrum. So if we expand this 0 to 4 kilohertz to here, we window it by drawing some overlapping triangles. These triangles get multiplied by the signal to generate another signal, I guess. So in this example, just the first two, the red triangle signal would look like this, and then be 0 throughout, and then the blue triangle would generate something that looks like that, and then be 0. And then we just integrate those signals, so in discrete format, we just add up all the samples. And this generates a matrix. So on our rows, we have the frequency axis. As you can see, like the red might be summed up to equal 500, the blue might be summed up to equal 1000, and then every row after that is another frame in time. So it's these frames that we talk about. And that generates an entire matrix. So this matrix kind of represents the position in space of that word. When we generate a dictionary, what we do is we generate this matrix for all of the data set, and then we average them together to get the dictionary coordinate. To calculate the comparison of a word that we're testing and a word in the dictionary, we calculate a cost d, which is just the Euclidean distance of all of these attributes for the test word subtracted with, or it's the Euclidean distance between the test word and the dictionary word, like the matrices. Something worth noting is that you don't actually have to calculate the square root, because the cost is, like, if you square all of the costs, they're all going to monotonically increase. So yeah, it's one operation you don't have to account for. The dictionary word that you iterate over that has the least cost is the one that we assume is the test word, and then we return that value.
Hi, today we will be demoing our ECE532 project, which is FPGA-based speech recognition. So we have 4 FPGAs. This is the load manager. Do you want to explain what the load manager is?
Sure. So the load manager basically receives a request from our desktop clients, and then it assigns the request to a separate compute FPGA. So in this case, the load manager will also display the request it receives on a VGA screen. So over here, you can just see the name of the program. Once we receive requests, it will show the requests down there as well, which we'll show you. Yeah, and then moving to the compute FPGAs, definitely.
Yeah, we have 3 compute FPGAs, these 3 ones. So please interpret the desktop and the FPGA separately. I'll show you one example here. So this is the audio file that we will be sending. Hard to hear, but it says poll naive. And now I will be sending that. And let's look at the load manager. It says request from sent to.
So it says request received from an IP address and then sent to a particular IP address. And then you can also see now that it identified the 2 words, poll and naive, that we sent, and it displayed it on the screen.
Yeah. We'll do a few other examples, right?
Yes, we can do one more on this one. So over here again, we have a similar thing going on where we send a request from the desktop. This is all of the packets that were sent, Ethernet packets, and it's now sending a compute request to a separate compute FPGA. So when it does that, it's actually sending it to this one right here. So you can see that in the terminal over here, words are being processed. It's identifying the 3 words that we sent, and now these 3 words will show up on the load manager again.
You want to play the audio?
Yeah, sure. I can play the audio real quick just as a confirmation.
Red, naive, tall.
There we go. Yeah, and one last example maybe over there.
Sure. So here we have this audio,
Red,
just red, and I will be sending that. We can look at the.
And now, there we go. Yeah, so that was our project. Anything you want to say as a conclusion?
I think that's all. Thanks
Yeah,
for watching.
Thank you so much.